In this video, we're going to look at limits at infinity. We're going to focus on polynomials. And as you can see below infinity, I wrote x goes to positive infinity and x goes to negative infinity. So for these limits, we are going to be walking on the graph forever in the positive x direction or the negative x direction. And what I'm curious about is if the graph is leveling off or blowing up. All right. So for polynomials, when we are given a polynomial, so I'm just going to make up one. That looks good. Okay, so if I make up a polynomial, the biggest power is called the degree. And the number in front, the coefficient, is called the leading coefficient. Okay. All the terms that come after the leading coefficient and the term with the degree are going to cause bounce and wiggles and bumps in your graph. But the main end behavior is determined by the front. So if I have an even power, so if the degree is even, then what will happen is that it will have end behavior on the ends that is up, up. Now, this is if the leading coefficient is positive. If the leading coefficient is negative, then it's going to go down, down. So, because this is a positive 4x to the 6th, it's going to go up, up. However, if I wrote that as a negative 4x to the 6th, then it would go down, down. Okay, so what we decide is based on the degree if it's even, and the leading coefficient if it's positive or negative. This is our rule. Okay, now if I changed it to something like an odd, okay, so, and some of you may have been noticing that I wrote odd, odd. It could be an odd even. It doesn't really matter. The leading term and its degree is what's most important. So if I have a degree that is odd, then it's going to go down and then up. And I'm putting this break in the graph because it could have bumps and wiggles depending on other terms. Okay, but it would go down and then up. And this is true if the leading coefficient is positive. So for this graph, it's going to go down and then up. Okay, if that leading coefficient is negative, it's going to reverse direction. Okay, so if this were a negative 4x to the 5th, it would go from up and then down. Okay, so what does this have to do with finding limits at infinity for polynomials? Well, if you know the end behavior of a graph, these can be really, really, really fast. Okay, so let me show you. So if we were to write the limit as x goes to infinity of 4x cubed minus x plus 17, okay, and I want to know what is my limit. So I want to know, does this graph level off? Does it blow up? Does it go really far down? So the leading term is an x cubed. It's positive. So from my little talk earlier, it's going to go like this. So as it approaches in positive infinity, it's going to go to positive infinity. That's the whole answer. If I was asked what the limit was as we walk to negative infinity, well, as we walk to negative infinity, it's going down. So here, the answer would be negative infinity. All right, pretty fast, right? Okay, what if we did an even? So what if I was asked to find the limit as x goes to infinity of 5x to the 4th plus 3x plus 8? Okay, because that leading term is even and it's positive, I know the ends go up, up. So that means that my answer as I walk to positive infinity, it's going to be going up. If I take the limit as x goes to negative infinity, well, as x goes to negative infinity, as I walk forever to the left, it's still pointing up. And there we have it. So limits at infinity for polynomials are very fast as long as you know facts about the end behavior. All right, good luck. I hope this helps with your homework.